Welcome to the course structure analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the 17th lecture. We started moment distribution method and we have derived the carryover factor for two cases. First case is a beam fixed at one end and then simply supported at other end. And then the second case is the beam is simply supported at both the ends. Okay, so these are the two cases are possible in a continuous beam when we are solving the problem by moment distribution method. So in that 60th lecture also we have discussed one numerical problem. Now we are going to discuss a different numerical problem. Okay, so in last class we discussed the problem with fixed supports. Now in today's lecture we are going to discuss about the simply supported problem. So analysis of continuous beam by moment distribution method. This is a second lecture and overall it is a 60th lecture. At the end of this lecture, the student can able to apply the moment distribution method effectively to the continuous beam problem, and then they can able to solve and draw the shear force and bending moment diagrams. And quickly I will take the numerical problem. So I am taking a simply supported beam, continuous beam, which is having three supports. Let's say support A, B and C. Support A is subjected to the eccentric point load of 3 kN and then the distance is 2 meters from the left support and this span is 4 meters, and span BC having the uniformly distributed load UDL of 1 kN per meter. Span AB is 6 meters long and span BC is 4 meters. Okay. So by using a moment distribution method, we are going to solve this problem and then we are going to compute the bending moment B. Okay. And then you need to draw the shear force and bending moment diagram also, that you can practice yourself, and then you can draw the shear force and bending moment diagram like a earlier problem. So we'll go by step by step. Step 1, we need to calculate the fixed end moment. So in the fixed end moment, we need to go span by span. So first I am taking the span AB. Let's draw the free body diagram, 6 meters, and then having the eccentric point load of 3 kN. This is 2 meters and this is 4 meters. This support A and then support B. Okay, so in these two fixed end moments I am going to calculate. This is MF AB and this is MF BA. These are the two fixed end moments we are going to calculate now. Let's calculate MF AB equal to, since it is an anti-clockwise moment, we need to use the negative sign. The formula is WA B square by L square. Okay. So let's substitute. W is 3 kN, A is 2 meters, B is 4 meters whole square divided by span is 6 square. Okay, so we'll be getting the value of minus of 2.67 kilonewton meter. Similar way, we can do it MF BA. The formula is plus W A square B by L square, and the W is 3, A is 2 meters square and B is 4 meters divided by span 6 square. So we'll be having 1.33 kilonewton meter. So don't forget to write the unit, it's very important, otherwise you will be losing the marks in the end semester examination. So how we have taken the span AB now? This is a span AB and then we are calculated the fixed end moment. Similarly, we are going to calculate the fixed end moment for the span BC. We are going to calculate for span BC. So let's draw the free body diagram first. This is support B. Support C. Span BC is subjected to the UDL of intensity 1 kilonewton per meter and the span is 4 meters. Now what are the fixed end moments? Fixing moments we are going to calculate MF BC, MF CB. First I am going to calculate MF BC equal to minus because of the anti-clockwise direction. Okay, so what is the formula? Formula is WL square divided by 12. So minus of W is 1, span is 4 square divided by 12. So I am getting minus of 1.33 kilonewton meter. Similarly, MF CB is equal to plus WL square divided by 12. We are going to substitute the same value only. So I am getting the positive of same 1.33 kilonewton meter. So the first part is now over. We have calculated the fixing moment or the fixed end moment. Now we need to go for the table where I can able to calculate the distribution factor. So listen carefully. I have to mention a joint. So this is our beam. So this is 6 meters and this is 4 meters. Let's mark this is A, support B, support C. So we are going to take a joint. Which joint is present here? Here the joint intermediate support we used to say as a joint. So I am considering the support B as a joint. From the support B, what are the members are connected? We have a member BA, we have a member BC. Now I am going to write the stiffness for this. So we know the stiffness is, for example, both the ends are simply supported. Both the ends are simply supported means the stiffness K is equal to 3EI by L. So you observe the problem, span AB is a simply supported, span BC also simply supported. So both the member I can use the stiffness is 3EI by L. For the span BA the L is 6 meter, for the span BC the L is 4 meters. Okay. So just I need to calculate the total stiffness here. Total stiffness is nothing but the summation of these two. What? The stiffness of span BA and then stiffness of span BC. Summation of these two is the total stiffness. The sum is 5EI by 4. Now I am going to calculate the distribution factor. So what is the distribution factor? For example, this is K1, this is K2. Stiffness of member 1 is K1, stiffness of member 2 is K2 and this is the total stiffness, let's say K. So here I am going to put K1 by K, here I am going to put K2 by K. So let's substitute K1 by K. K1 is 3EI by 6 divided by 5EI by 6 and then this one 3EI by 4 divided by total stiffness 5EI by 6. So you will be getting EI will be get cancelled automatically here and then the factor is here I am getting it's 0.4 and for the span BC I am getting 0.6. So in moment distribution method whether you are getting the values right or wrong easily you can able to check by adding the distribution factor for BA and BC, the summation should be equal to 1. So the distribution factor for any joint or any intermediate support if you calculate and add it for the two members the sum has to be 1 so that you can able to verify you are doing right. Suppose if the distribution factor is more than 1 or it's less than 1 then you are committed the mistake somewhere you need to correct it. So in this way we can able to verify. So what is the step 4? So step 4 we have to do the another table which is a moment distribution table itself. So let's complete that table. So we have a span A, span B, support A, support B and support C. Just now we calculated the distribution factor. Span BA is its 0.4 and span BC it's 0.6. Then we have to enter the fixed end moment which we are calculated. Let's go back and then you can see we have the fixed end moment of for example minus of 2.67 and then 1.33. So this is minus of 2.67. This is MFAB and then MFBA is plus 1.33 and then MFBC is minus of 1.33 and then MFCB is plus 1.33. Now what is the issue we are going to face it here? We know this beam is having the simply supported connections at the A and B. You see here, support A is simply supported, support C is also simply supported. But in the table you can able to observe we have the moment here and we have the moment here. We need to eliminate that moment. How to eliminate that moment? It's very simple. Whatever the value we are having, we need to write the positive of that here. So plus 2.67. I have a negative 2.67. So I am writing plus 2.67. Here I have the positive 1.33. I am going to write minus of 1.33. Then you see in this the 50% of the moment will be transferred to the intermediate support. 50% means the 2.67 by 2. So which is 1.335 and this half is 0.665. Now we need to draw one line and then sum of the moments at A is become 0 and sum of the moment at C is become 0. So now we satisfied the simply supported condition. Only intermediate span going to have the moment. Okay. So what is the next step we are going to do here? We just need to add these two values. I am doing that operation here. I am just going to add 1.335 and then minus of 0.665. Okay. The summation of this multiplied with 0.4. That I need to write it here and then 1.335 minus 0.665. The summation of this multiplied with the distribution factor 0.6. That I need to write it here. So if you do this operation, you will be getting 2.665 here and then here minus of 1.995. Okay. Before this, one step has to come. Let me clear this. So that step is we need to sum up these values. So what value we need to sum up? This value and this value plus this value and this value plus. Then only we need to do the operation what I have done here. So let's add this value. We'll be getting 2.665 of summation of this and then the summation of this is minus of 1.995. Now I am going to do this operation. So what I have to do? I have to add 2.665 minus of 1.995. This value multiplied by 0.4 which is minus of 0.268. Okay. And similarly I need to add 2.665 and then minus 1.995 multiplied by the distribution factor of BC is 0.6. So that value is minus of 0.402. Now we can able to observe I cannot able to transfer this moment to the any support because support A and support C are the simply supported condition. We cannot able to proceed any further steps. We can sum up the value, we will be getting the final moment. So I am just going to sum up this value and sum up this value. Let's see. Here I am getting plus 2.4 and here I am getting minus 2.4. So equilibrium condition is satisfied. MBA plus MBC is equal to 0. So if you add these two moments, we will be getting the final moment. Now write the final moment. So MAB equal to 0, MBA equal to plus 2.4, MBC is equal to minus 2.4, MCB is equal to 0 because these two are 0 because simply supported condition. And if you put this MBA plus MBC will be getting 0, equilibrium condition satisfied. So by using this moment, you can calculate the reaction forces and draw the shear force and bending moment diagram. Try it yourself by following the 15th lecture. So in that lecture, we are already discussed one problem. Very clearly, we discussed about how to draw the shear force and bending moment diagram by using the moments for a continuous beam. So in this lecture, we have discussed how to calculate the final bending moment for continuous beam by moment distribution method. So that's about the moment distribution method. Next lecture, we are going to discuss about the theorem of three moment equation derivation. Followed that, we are going to solve the continuous beam problem by using the Kepler-Hahn theorem of three moment equation. Okay. So thank you for watching this lecture. Thank you. We'll meet in next lecture.